think of space, we naturally think of the stars, solar systems, galaxy, the distant reaches of the universe.
But space has another dimension to explore, not outward, but inward, into all the basic elements of everything there is on our planet.
Here, a miniature world of space exists, a world filled with constant motion, one that went undetected for centuries. It is the world of the atom.
Deep within the atom lies the origin of one of the most important issues of our time. For with the discovery of the atom's power came the birth of the nuclear age. The building behind me is a nuclear power plant generating electricity. Advocates of nuclear energy see this facility as economical, safe, clean, and necessary.
Others believe such plants to be dangerous, at best a threat to health, and at worst a potential source of catastrophe. How can tiny atoms generate electricity and at the same time create such wide differences of opinion? We'll find out as we take a closer look at the atom.
We'll begin by watching an Arabian Nights fable, which in some ways is very much like our own story. Do you remember the tale of the fisherman and the genie? One day, a fisherman was casting his net when he happened to pull ashore a brass vessel. Its top was closed with a lead stopper. Surprised at his strange catch, the fisherman said,
"I'll wager that whatever is sealed so well must contain something of great value."
Know that presently thou wilt have to die.
Heaven forbid, or at least tell me why.
As I lay imprisoned in that tiny jar for many centuries, my anger grew and grew until I swore in my heart that my liberator should perish.
What a cruel trick fate hath dealt me. Trick? Oh, genie, since thou art determined upon my death, grant me this one last question.
Well?
How can one as mighty and powerful as thou dwell in so tiny a vessel?
What? Thou dost not believe me?
Not till I have seen it done can I believe it.
Watch then.
Now you shall return to the sea.
Nay, nay. I did not mean what I said. Let me out, and I will serve you faithfully.
Faithfully?
You in turn must respect me, for remember how awesome is my power.
Like the fisherman, we have released the awesome power of a genie, an atomic genie.
Unlike our fable in which one man discovered the genie, we owe our knowledge of the atomic world to many people. Science often takes an evolutionary path. The work of one scientist eventually contributes to discoveries made by others. One of the first to propose an atomic theory was John Dalton, an English chemist. He suggested that an atom is like an indestructible ball held together by some unknown force.
I believe that everything is made up of atoms, and the atoms in one thing are different from the atoms in another. Also, many things are mixtures of different atoms.
How nature creates these mixtures was first understood through the work of this man, Amedeo Avogadro of Italy. Avogadro suggested that when atoms of different elements combine, they form into larger units, which he called molecules. For example, when one atom of oxygen combines with two atoms of hydrogen, they form the most familiar molecule in nature, H2O, water. Then a French scientist, Henri Becquerel, made an important discovery while working with the natural element uranium.
I left a piece of uranium on a wrapped photographic plate in a dark drawer. When I developed the plate, it was fogged. Uranium seems to possess some mysterious activity and give off some kind of radiation.
Becquerel had discovered the effects of radioactivity, but he didn't know what he had found. Becquerel's discovery so intrigued two other French scientists, Pierre and Marie Curie, that they began trying to find the source of this radiation. In the course of their investigation, the Curies discovered two more radioactive elements, polonium and radium. They found uranium, polonium, and radium to be an almost endless source of radioactivity. Scientists were baffled. How could a tiny mass radiate energy?
This man helped solve the mystery, Albert Einstein. He proposed a theory which showed that every mass contains a tremendous amount of energy. His theory is expressed in this famous equation.
E stands for energy, M for mass, and c squared is the speed of light multiplied by itself. Now, c squared is a very great number, and so it means that a small amount of mass can be changed into a very large amount of energy.
Einstein, like the fisherman, found that a mighty force was contained in a small vessel. The next atomic clue was discovered by a British physicist, Ernest Rutherford. Rutherford realized that the particles being thrown off from radioactive substances were much smaller than the atom itself.
I aimed these particles at a thin leaf of gold and found unexpectedly that they passed right through it. Then, one out of thousands of particles struck something solid and ricocheted. I can only conclude that the atom is mostly empty space, with something solid and very small in the center. I shall call this tiny object the nucleus of the atom.
Think how small the nucleus of an atom must be. There are billions upon billions of atoms in this tiny pencil dot. If we were to enlarge one of these atoms to the size of a football, the nucleus would still be too small to see. If we were to enlarge one to the size of a football stadium, the nucleus would only be as big as a grain of sand.
With Rutherford's discovery of the nucleus, we began to have a better understanding of the structure of the atom. The shell of the atom appears solid, just as a fast-whirling fan seems solid. Actually, the shell is composed of a swarm of tiny electrical particles called electrons. They circle around the nucleus like planets around a sun, so the atom is like a tiny solar system. Next, scientists began to probe the atomic nucleus for its secrets. They found that it was composed of small electrically charged particles. They call them protons, which means primary particles. Later, another particle was discovered in the nucleus, but this one had no electrical charge. It was neutral, and so it was called a neutron.
Atoms are always in balance. For example, an atom of the simplest element, hydrogen, has one proton in the nucleus, and to keep it electrically balanced, one circling electron. The next element, helium, has two protons and two circling electrons. There may also be neutrons in the nucleus that add to its weight. And so, by simple addition, nature builds the atoms of all elements. For carbon, 6 protons, 6 electrons, and some neutrons. And 16 for sulfur. (26) iron. (47) silver. (79) gold. 92, uranium, the famous radioactive element. Here, nature has crowded so many protons and neutrons into the nucleus that it becomes unstable. It tries to stabilize itself by throwing out small particles and rays. This natural activity of the nucleus is what we call radioactivity.
So, radioactivity is the spontaneous natural decay of unstable atoms. When this decay, or breaking down, occurs, there's a small change in the nucleus which creates energy. This energy is released in the form of radiation. We might say that a radioactive atom is like a set mousetrap. Both contain energy. A table covered with mousetraps represents the atoms in a piece of uranium. Every so often, one breaks down all by itself, releasing a small burst of energy. In uranium, this energy is called radiation. Radiation from the atomic nucleus cannot be seen, heard, or felt. To detect its presence, special instruments were developed. One is the Geiger counter. Another is the cloud chamber. Here, a tiny bit of uranium is giving off a constant shower of radiation. Inside the cloud chamber, radiation leaves visible trails. Each new vapor trail shows that another atom has released some radiation. Since there are so many atoms, this activity appears to go on almost endlessly.
The three most common types of radiation emitted by radioactive elements are alpha particles, beta particles, and gamma rays. Alpha particles travel only a short distance and can be stopped by the skin or a sheet of paper. Beta particles are more penetrating. Some can pass into the skin, but can be stopped by thin sheets of metal. Gamma rays are the most penetrating of the three. Gamma rays are similar to X-rays and can pass through the skin. They can be stopped by materials such as lead, concrete, or even water.
In the early days of nuclear science, little was known about the effects of radiation. Now, after more than 50 years of research, we know a great deal about how radiation can affect us. Certain levels of radiation can harm the human body. Exposure to very large amounts of radiation could cause illness, genetic damage, or death.
There are many sources of radiation. The most widespread is known as background or natural radiation. Most of it comes from our planet, the sun, and outer space. We're continually exposed to it and always have been throughout history. Natural radiation is in the air we breathe, the food we eat, the water we drink, the homes we live in, and the earth we walk on. Even our bodies contain some radioactive elements. Natural radiation accounts for about half our total annual exposure. Some sources of radiation are man-made. Nearly all of this exposure comes from medical and dental X-rays and radioactive drugs. Other man-made sources include clocks and watches with luminous dials containing radium, smoke detectors using radioactive materials, color television sets, low-level emissions from nuclear power plants, and nuclear weapon production and testing.
Sometimes scientists conduct experiments and do not immediately realize the importance of their discoveries. This was true of Felix Strassmann and Otto Hahn, two German scientists, whose work was later interpreted by Lisa Meitner and O.R. Frisch. In their famous experiment, Hahn and Strassmann aimed a stream of neutrons at atoms of uranium. Since neutrons are neutral particles, they were not deflected by the atom's electrical charge. They passed right through until finally a neutron struck a nucleus. The uranium nucleus split in two. Nuclear fission had been accomplished. But that's not all that happened. When the nucleus split, two neutrons were released, and two new atoms, called fission products, were created. So now there were two neutrons to split two other uranium atoms. This implied the possibility of a chain reaction in uranium. Let's go back to our mousetrap experiment and create a chain reaction we can watch. We'll use two ping-pong balls for neutrons that will be released when the atom splits. Now these mousetraps are the atoms that will be in the game. They're all set, loaded, and ready to go. Now, to start the chain reaction, all we need is one neutron. It has to trigger just one trap. The ping-pong balls that are released will set off 2 other traps, and then we'll have 4 balls flying to trigger more traps. Well, I think you can guess what's going to happen. Watch. An atomic chain reaction works in exactly the same way. But for a chain reaction to be useful, scientists had to find a way to control it. Let me show you what I mean. Our mousetrap chain reaction can be slowed down with the aid of a slow-motion camera. Just as the chain reaction of ping-pong balls is now spread over a longer period of time, the fission rate in an atomic chain reaction can also be slowed down.
The scientist who first achieved a sustained nuclear chain reaction was Enrico Fermi, who had come to America from Italy. He demonstrated that a chain reaction could be controlled. Others used his work to develop the atomic bomb at the height of World War II.
Fermi's work also made it possible to harness the atom for peaceful purposes, to use it to generate electricity. To understand how today's nuclear power plants work, let's return for a moment to the atom. This picture shows atoms of hydrogen and oxygen combined into molecules of water. Let's pretend these molecules are magnified so we can see them. Atoms and molecules are in constant motion. When heat is applied, the water begins to boil. See how the molecules jump away from the surface as steam? In steam, the molecules are moving with great force, enough force to bounce the lid of the coffee pot. When these molecules of steam exert their power against a piston, they can turn a wheel. It was the power of steam that turned our generators and took us from the gaslight era into the age of electricity.
Today, plants utilizing nuclear fuel provide a large share of electric power to cities like Chicago, London, Hamburg, Tokyo, Buenos Aires, New York, and many others throughout the world. If we compare energy sources, it would take about 1,780 pounds of coal to equal the energy in one nuclear fuel pellet the size of the simulated one, or 149 gallons of oil, or 157 gallons of regular gasoline.
The mechanical principle of nuclear-generated power is similar to that of any steam-powered generator. The basic difference is the source of heat used to produce the steam that spins the turbine generator. Instead of burning coal, oil, or gas, the nuclear power plant has a reactor containing a core of nuclear fuel, primarily uranium. The uranium is used to create heat by setting up a chain reaction. To regulate the chain reaction, control rods that absorb neutrons are inserted in the reactor. These rods catch some of the flying neutrons and take them out of play. This causes fewer atoms to split and keeps the reaction controlled at an even rate. The fission process heats water, which is then run through a boiler under pressure, where it produces steam. Steam for power. These reactors are called PWRs, meaning pressurized water reactors. Other types of reactors are also in use, such as boiling water, gas-cooled, and heavy water reactors.
To contain the heat and radioactivity being created in the reactor, safety precautions must be taken in the design and construction of a nuclear power plant. Several barriers are built into the plant to help prevent harmful releases of radioactive materials. The first barrier is built into the fuel itself. Uranium fuel is made of hard, dense ceramic pellets. These retain the solid fission products. The pellets are encased within metal tubes or cladding to prevent the gaseous fission products from escaping the fuel. Another barrier is a steel pressure vessel with walls about a half-foot thick. This holds the core which contains the fuel and control rods. Each reactor is encircled by a thick concrete wall which supports the vessel and provides a shield against radiation. A second steel shell also encloses the reactor. This shell is designed to help prevent the escape of radioactive materials in the event of an accident or failure. A 4 to 7 foot thick outer wall of steel reinforced concrete acts as another radiation shield and as a protective cover against outside dangers, such as air crashes or sabotage.
Of course, a nuclear reactor is a machine, built and operated by human beings. But machines aren't perfect, and people can make mistakes. A nuclear reactor cannot explode like a bomb, but it does create radioactive material, which decays and generates large amounts of heat. This combination has caused concern about a meltdown of the reactor core. This might happen if water, which is used to cool the reactor, is lost, either through mechanical failures or human errors. Without cooling water, the temperature could become so high that the fuel would melt and turn into something like molten lava. Critics of nuclear power claim that the fuel could then melt through the steel and concrete containment vessels, releasing dangerous radiation into the air or ground.
Advocates point out that nuclear power plants have multiple cooling systems and backup systems designed to cool the core and prevent a meltdown. Even if a meltdown were to take place, they believe there would be no dangerous release of radioactivity.
Another area of concern is the disposal of radioactive wastes. Generally, there are 3 types of radioactive waste created in the routine operation of nuclear power plants. First, certain amounts of radioactive gases and liquids are released. Under normal operation, they are small compared to the natural background radiation in our environment. These controlled releases are monitored and regulated by law. Secondly, there are low-level radioactive solid wastes, such as clothing, used work gloves, shoe covers, and pieces of machinery contaminated with radioactivity. These wastes are put in containers and transported to disposal sites where they are buried along with similar radioactive waste from hospitals and research facilities. Third, there are highly radioactive and potentially dangerous fission products in used nuclear fuel. Generally, once a year, a portion of the fuel elements in the core must be replaced. The radioactive fission products contained in the fuel must be carefully isolated from the environment. At most nuclear plants, used fuel is temporarily stored underwater near the reactor. Water provides a radiation shield to protect the operators and also serves to cool the fuel. After a cooling period underwater, during which the radioactivity is greatly reduced, used fuel elements are placed in shielded shipping casks. These casks are transported to special storage facilities, or in some countries to reprocessing plants. These plants separate and recover uranium and plutonium from used fuel.
We know fission products break down and with time become non-radioactive, but high-level waste is highly radioactive for long periods of time. It must be isolated for hundreds of years. Unreprocessed used fuel must be isolated for thousands of years. The long-term storage of high-level waste is one of the most important issues associated with nuclear energy. Several methods for disposal of high-level waste are being evaluated. One is deep underground burial in a place such as this granite formation in Sweden. In France, a commercial glass plant for encapsulating high-level waste has been operating for several years. In the United States, studies are underway for locating and qualifying underground formations. No matter what method of disposal is used, some people believe that before waste had decayed to a harmless point, they could escape, either through accident or sabotage, and create a hazard by releasing dangerous radioactive materials into the environment. Others believe that the technology of safe nuclear waste disposal is available and not difficult. They say that waste can be combined with glass or ceramic. In this form, waste would be solid, stable, and durable. Additional protection can be provided by placing the glass in welded metal cans. These containers would then be placed in geologically stable areas which have experienced no earthquake activity for millions of years. Finally, they feel that even if a nuclear disposal site were disturbed, waste would not move very far, if at all.
How safe is the use of nuclear energy? The question is a complex one. Perhaps we should ask, what is the safety record of nuclear power plants? Do the benefits of nuclear energy outweigh the risks? Then we must ask, are other sources of power available to meet the world's growing energy needs? Is it possible to develop new sources of energy? And what are the comparative costs and risks involved in these options?
One thing is certain. The tiny atom will continue to influence the world we live in. In industry and agriculture, our knowledge of the atom serves us in many ways. In medicine, doctors are using radioactive isotopes for early diagnosis of heart disease and in the treatment of cancer. Brain images can now be viewed and measured by means of an atomic process called tomography. We can now determine the age of prehistoric artifacts by using the atoms in radioactive carbon. And today, the atom is producing electricity to serve millions of people.
As it always has done, knowledge of the tiny atom continues to broaden and deepen our view of the world. Just as scientists first explored the atom, radioactivity, and nuclear fission, scientists today are discovering new dimensions of an even tinier world. They've discovered that the atom is made of more than just electrons, protons, and neutrons. They've broken through to a world of high-energy subatomic particles, tiny energy masses with names like quarks, gluons, and leptons. Like the fisherman in the fable, we've released a genie, an atomic genie. And as we've seen, its power is awesome indeed. It can do our bidding in many ways, to create or to destroy.
But our genie is in itself neither good nor evil. It is our responsibility, yours, mine, everyone's, to determine how this genie, released from the tiny atom, can best serve us in the future.